Well, good morning, everyone. Welcome back to Calculus. It's so good to be with all of you again. When we were together yesterday, it was a whole bunch of 5-minute conversations, and I got to say, I really appreciate the chance to talk to all of you face to face, or at least voice to voice, for a few minutes each day. Lots and lots of good work. I think about the only consistent issue people had was around the recurrent formulas for sequences. Lots of folks just forgot that you need to sort of initialize the terms and set what your first term or your 0th term is equal to. But otherwise, I think the work was pretty much uniformly good. So keep up the good work. I'll try to get those grades into my labs tonight if I can do that. That was yesterday. When we were together again last week, or when we were together last week, we talked about the comparison tests, and I think it was a good session, but also perhaps left a few of you a bit in the dark on what to do and what to compare to. So we'll try to bring some light into the room on that. But before we dive into the comparison test, just a few reminders. Let's dive into our new material. Again, we're talking about the comparison tests, and there's 2 comparison tests that we're talking about in this section. We're talking about direct comparison, and then also we're going to be talking about or introducing what's called the limit comparison test, which is quite a bit more powerful and actually easier to work with. So let's start by looking at the previous example that we worked at, just kind of reminding ourselves of where we were at. So when we were last together, we looked at this series where we wanted to know if the sum from 1 to infinity of 1 over root n times 3 to the n was convergent. And so what we did was, thank you, Enrique, for clarifying and explaining the holiday. I appreciate that. So what we did was we said this unknown series is less than or equal to this geometric series, which was convergent. Since the one above converges, goes to a number, the one below must also converge by the comparison test. So let's look at the second example in this section, and we can do that on paper. So on this particular example, this is example B in section 10.5. We have the sum from 1 to infinity of 1.
I think you're still screen sharing.
Ooh, clever. Stop share. Thank you. Let me try that again. On this particular example, example B, we have the sum from 1 to infinity of 1 over n squared plus 3, quantity raised to the 1/3 power. And as we learned last time, that if we want to figure out what to compare to, we usually try to just ignore all these extra terms that are out here. And so we might compare to the sum from 1 to infinity of 1 over n to which power?
2/3?
To the 2/3 power, exactly. Squares gives you the numerator, like 2/3 power. Just imagine ignoring the plus 3 that's in there. And what can you tell me about this series? Does it converge or diverge?
It should converge.
Converge.
It's the other converge.
Diverge?
It diverges by what? What kind of series is this?
P.
It's a P series. And when does the P series converge?
When
P is greater than 1.
When P is greater than 1. So in this case, we have P less than or equal to 1. That makes sense? So this, as to why it diverges. So in this case, what we have, if you think about it graphically, is we have this series 1 over n to the 2/3, which is going to be, maybe if I think about this one as being pink, so it's going to come in like this, and we're going to add up all those terms. Or that would be one way of putting it. These are the terms. And then if you add up all those pink terms, so if you add pink, what do you get? You add all those lengths, since it diverges.
If it diverges, wouldn't it be infinity?
Exactly. So we get infinity. Okay. So then if we come to the original, okay, where does the original live relative to the pink? And specifically, is it above or is it below the pink?
Above?
Be below
Below.
Yeah.
because you're adding it to the
Great.
denominator.
Yeah, we're adding to the denominator, which makes the fractions smaller. So bigger denominator means smaller things. So our pink stuff is down below each time.
Blue.
Or sorry, blue, thank you. Apparently I'm colorblind in addition to other things. Okay, so this tells us that the blue stuff is less than, this is a really important inequality, is less than the pink stuff. So the blue is less than infinity. Tell me a couple numbers that are less than infinity.
2.
Infinity minus 1.
Infinity minus 1.
Infinity minus
Yeah.
1, right? So this could be 2, in which case it would converge, but it could also be infinity minus 1, which is infinity, which also diverges. So in this case, we would say that the comparison test is what? What's our term for this?
Inconclusive.
Inconclusive.
Inconclusive. It's the worst. It's like we almost have something to compare to, but the inequality goes the wrong direction. And because the inequality goes the wrong direction, we just sort of don't learn anything. Super, super frustrating. Questions about this?
I guess, like, how can we tell if it's just inconclusive or if we were maybe comparing it to the wrong thing?
Well, usually you're comparing to the right thing because the two series look pretty similar to each other. And so usually you could get inconclusive and be comparing to the wrong thing. That's possible. But most often you're going to get inconclusive when you're comparing to the right thing, but it's just not a very helpful comparison because the inequality is going the wrong direction. Let me screen share again and show this little chart here. I think that this helps a little bit. So when you're doing the comparison test, you're comparing against a known series. There's two really common known types of known series. What are the two biggest known series?
Geometric and arithmetic.
Geometric is one. Yep.
P.
Yep. So geometric and the P series.
Harmonic?
So the harmonic series would be an example of a P series. So we could also call it the harmonics. I mean, we could include that, but if we just want to be super simple, we'd say most of the time your known series is going to be one of these two options. It wouldn't have to be, but most of the time. if your known series is bigger, okay, and your known series converges, then the unknown series is going to converge. If your known series is smaller and the known series diverges, then the unknown diverges. So in the case that we were just looking at, the known series was the sum of the 1 over n to the 2/3, and it lived in which of these boxes? Top or bottom, left or right?
The one we knew was bigger.
Mm-hmm. Yeah, so it lived in this. It lives in this box right here because the known series is bigger. It diverged, which left us with an inconclusive result, which is kind of aggravating. Right. Good news is coming, but we're not quite there yet. I know I didn't fully answer your question yet, Melissa, but other questions before we go on?
I just posted one on the chat.
Yeah, thank you, Titus. So Titus connected this back to Calc 2, where you did comparison tests. And that's exactly right. This is exactly like the comparison test you did in Calc 2 for improper integrals. But what we're going to see in a few minutes is that we actually, with our limit comparison test, we actually have more power than we had in Calc 2. Phrased another way, I think this comparison test that we're talking about now is relatively easy to understand, but I would actually suggest that you don't use it very often. I think it's not very helpful. The limit comparison test that we're about to talk about is less intuitive, but way more powerful because you don't have these inconclusive categories to worry about. Questions? Very good. All right. Let's look at another example where we use the comparison test to try to determine the convergence of a series. So this is example 2 in 10.5. So I want to look at the series from n equals 1 to infinity of the fraction, or the rational expression, n squared over n to the 4th plus n minus 10. And I think that it should be clear, kind of right from the get-go, that we would like to compare with a p-series. We'd like to compare to the sum of the 1 over n squareds from n equals 1 to infinity. But there's some mixed messages happening in this particular expression. So notice the plus n is going to create a few issues for us. So if we have the sum of the n squareds over n to the 4th plus 4 or plus n, here we're adding to our denominator. That's going to make the whole fraction smaller. So this will be nice. This will be less than the sum of the 1 over n squareds. This one converges. And so since the bigger one converges, all will be good to go. Unfortunately, the minus 10 seems like it goes the other direction, right? Because if we had the sum of the n squareds over n to the 4th minus 10, this would make the denominator smaller, which makes the whole fraction bigger. And so this would be bigger than the sum of the 1 over n squareds. And so this would make the the comparison test inconclusive. Very good. So it's like the red plus n and the minus or the green negative 10 are like fighting against each other. And in one of them is going to help us with our comparison test, and the other one seems like it's hurting our comparison test. So what are we supposed to do? And so what I would propose we do is we make the following observation. So notice that when we have n, when we have small n's like n 0, 1, 2, 3, 4, 5, so when n is small, then that minus 10 has a fair amount of influence. So when n is all the way up to 10, that minus 10 seems like it's controlling things. So let's split out that the parts where the negative 10 can win from the whole series. And we will separate from that the place where the n's don't win, or where the n wins. So notice that from 11 on and on out, the n will be bigger than the minus 10. Since the n is bigger, that means the denominator is larger, which means that the whole fraction will be smaller than 1 over n squared. And so what we can do by this approach is we can take some of those problematic pieces that are in the argument to our series, and we can put them within a finite partial sum. So finite partial sum. And since that finite partial sum is equal to a number, we can then allow ourselves to just look at the infinite series where the terms that we care about are dominant, are working. And so here, for the bigger n's, the minus 10 doesn't do anything. The plus n just makes things smaller. So we can indeed compare to the 1 over n squared. And so we have a number plus a convergent p-series. All of this stuff is bigger than the original series. And so the series we care about converges by the comparison test. Once again, the main point is that if you have this tug of war happening between positive terms and negative terms, and you don't necessarily know which one is going to win, you have the option or the choice of separating out or breaking out the first part of the series and dealing with that separately from the infinite series. And so get rid of the confusing stuff at the beginning and then just focus in on the end on your path to determining whether the series converges or diverges. All this is going to become a moot point in just a moment as we learn about our limit comparison test, but this is in general a valuable tool to have in your toolbox as you learn to understand whether infinite series converge or diverge. So, good question. All right.
Quick question.
Titus, go ahead.
Does a simpler way involve the ratio of the leading coefficients? Just ask.
No, the simpler way is going to involve what's called the limit comparison test, which is where I want to go next. The problem with the comparison test is that you end up with these two bad boxes, and you end up having to deal with things like little terms at the beginning and going, what happens with those little terms at the beginning? It's just an awkward test. to actually implement, even if it's intuitive, or I would say it's intuitive. So the limit comparison test works as follows. So the limit comparison test, suppose that two series, A and B, are series with positive terms. If the limit of the ratios is equal to a constant, then either both series converge or both series diverge. That is, I always describe it as they share the same fate. Notice it doesn't matter whether you have A over B or B over A. Like if you compared this to the limit as n goes to infinity of Bn over An, this would just give you, in this particular case, it would just give you a 1 over C. It's still a constant. They're still going to share the same fate. So the order of the A's and B's is not important. What matters is, does the limit of their ratios equal a constant? Many of you in Calculus 3 dealt with the ratio test with power series. This is not the ratio test. This is a different test. This is the limit comparison test. Super powerful. Let me show you a movie which I hope will help you understand what's going on a little bit here. So I'm going to So I made you a little movie this morning. It's 1.5 minutes long.
I believe this is your floor.
Oh, thank God. How'd I get myself into this?
God, Dyna guy. Oh, he had a great look. Oh, the cape and the boots.
No capes.
Isn't that my decision?
Do you remember Thunderhead? Tall, storm powers. Nice man. Good with kids.
Listen.
November 15th of 58. All was well, another day saved, when his cape snagged on a missile.
Thunderhead was not the brightest bulb.
Stratogale, April 23rd, 57. Cape caught in a jet turbine.
You can't generalize about that.
Metaman, express elevator. Dyna guy, snag on takeoff. Splashdown, sucked into a vortex. No kicks. No, go on. Your new suit will be finished before your next assignment.
So in the comparison test, the limit exists, they have the same fate. Let's see. Okay. Did the video come through? Can you somebody talk to me? Okay,
Yeah.
cool. Okay, here's the deal. So here's the deal with the limit comparison test. What you're going to do is you're going to try to take some unknown series. Think about that. That's your Lois. That in the first video clip. That's your superhero in the second clip. And you're going to try to tie it to something that's known. In the first case, we're tying it to Superman. Everybody knows what happens to Superman, right? Superman's always going to win. He's always going to save Lois. It doesn't matter what scrape Lois gets in, Superman will always be able to save her. That's how the movies always work. And so we're going to try to take Lois, regardless of what scrape she's in, Lois is going to be fine because we tied her to Superman. Same thing And I think about Superman saving things as convergence, right? That's the good, happy ending. Then in the second clip, everybody's favorite no capes Edna line, you have this superhero like, oh no, what's going to happen to that particular superhero? They've got the cape gets sucked into whatever the thing is, gets caught on whatever the snag is, and because the cape gets snagged, it drags the superhero along with it. The cape's path diverges towards end of bad story, so the superhero also has a bad ending to their story. Okay. You say, well, how do you connect the things together? You connect the things by showing that this limit exists. So let me do a couple of examples with this. So here's the example that we were just fumbling around with a little bit. And we say, we don't know what's going on. We're confused. We don't know what to compare to. The fact that these small terms are in there, I don't know. This is sort of frustrating, annoying. But we do know what we want to compare to. So what are we going to compare to?
Superman.
Superman. And in this case, what's our Superman?
Some 1 over n squared.
1 over n squared. And does Superman converge or diverge?
Converge.
Converges. Okay. So this is what we're going to compare to. Now we have to see if they're tied together. Okay. So to do that,
take limits.
We have the limit as n goes to infinity. It doesn't matter the order. So 1 over n squared over n to the 4th minus n minus 1 over 1 over n squared. So in this case, I have those terms in the numerator. I have these guys are in the denominator. Is that a simple enough limit that we just know what it equals? Do people just see this?
Yeah.
So what's this limit equal to?
0.
1.
Yeah,
One.
it's the 0 called 1. Exactly.
You just multiply by the reciprocal, and now your leading coefficient of the
Now I've got an n to the 4th over n to the 4th. Exactly. The fact that it's 1 is not so important. What is important is that this is a number. I don't care if it's 1 or 5 or 17 or -3, but what I care about is that it's a number. The fact that it's a number tells us what?
That it converges.
Doesn't tell it. It tells us that they share the same fate.
Right, share the same. Yeah. And I'm sorry, what was they share the same fate? But what was the scientific term for it? Expression.
The scientific term. How did I put it in the notes? It says either both series converge or both diverge. Yeah.
Okay, thank you.
Basically, there's no fate involved, but basically both converge, both diverge.
Yeah, it helps remind, but thank you.
It means at some point in the future, they both meet at the same point?
No.
Or that they both get really close?
It means that they're close enough together to have the same fate. Yeah, exactly. Just like in order for Superman to save Lois, he's got to be close. In order for the cape to drag the superhero in, they've got to be, the cape has to actually be attached to the guy's neck or whatever. So they share the same fate. The green one's fate is convergence. So since the sum of 1 over n squared converges, we get that the sum of the n squared over n to the 4th minus n minus 1 converges. And what test is this by?
Limit comparison.
By the limit comparison test. Exactly. Questions?
Sure. So by the same fate, we're agreeing that the both limits converge in whatever number, like that's fate, right?
No. Wait, can you say that again?
Like, so by sharing the same fate, we agreed that eventually both of them are gonna converge at a point. Doesn't really matter which point exactly, provided both of them converge anyway, right?
Not necessarily. So, for example, I mean, let's do like a super simplistic example. Suppose we have the sum of 2 over n squared from n equals 1 to infinity. And so suppose we decide we want to do a limit comparison test, LCT. And I want to do this with 1 over n squared. Okay. So the limit as n goes to infinity of 1 over n squared over 2 over n squared would be what?
A half.
A half. So, but I think it should be, so what does this 1/2 tell you?
There is a commonality.
So it tells you that it tells us that they share the same fate. They either both converge or they both diverge. So in this case, it's saying that I just want to copy my same wording. Since the sum of the 1 over n squareds converge, we get that the sum of the 2 over n squareds converge by the limit comparison test. Tell me about this tells me they both converge. What does it mean for a series to converge? That means that it equals, what does it mean it equals?
It equals some value and not infinity?
Yeah, it equals a number at the other end. So using your complicated skills you learned in kindergarten, or maybe it was 3rd grade, like if this one's 1 over n squared and this one's 2 over n squared, are they going to equal the same number? No, probably this one's probably going to be twice as big as the other one, right? So it's not the same number, but what the limit equaling 1/2 says is it's more like it says that they remain a similar distance apart. Like that maybe they come to the exact same place, but more likely they just remain a similar distance apart from each other. And so since they're a similar distance apart, the fact that one converges must mean the other one converges, or vice versa. And that's why the little -1s and +1s and things like that don't really matter in this case, because I don't really care if things are above or below. I just want to know, are things about the same distance apart, which is what the limit comparison test gives me. Questions?
So if I understand this, we're basically doing the comparison test, but instead of just knowing whether or not it's similar to the original function, we can actually determine if they are following the same path. And if we know because we know whether or not the compared equation is convergent or not, then we can apply that to the original equation and say that converges or not.
I think so. It's like the comparison test without inequalities. Like these are the hardest parts of the comparison test, is trying to figure out, like, is it above or below and all that kind of stuff. So let's just get rid of that part of it and just focus on the meat of the comparison, like you were saying. do another example?
Sure.
Well, actually, let me put you in breakout groups because this shouldn't be that difficult, but I feel like let me just see if there's some questions, if people are tracking with what's going on before we do another one. So let me just put you in groups for just a couple minutes.
Robert, yeah, you were saying?
Well, so that number that you get out of this comparison, it doesn't show you a value where they converge together. All it's doing is it's setting up. It's almost like it's setting up a ratio of their convergence. It's not giving you something. You can't calculate what number they converge at. It's just telling you that they do converge at some ratio of each other. That's all we're getting out of this.
Yep.
And we don't really care about that ratio.
No, all we care about is it's a number. That's it. If we see a number, we know we're good, because if we can evaluate one, we know something about the other. That's the big takeaway from this.
Yes.
It's about solving convergence. It's about determining what the series does way out at the end where we can't reasonably calculate.
So like the idea is if we don't get a value, that means that either like the denominator goes into infinity or the numerator goes into infinity of that ratio.
Probably. If you don't get a number, what it means is you have a bad comparison.
Yep.
So it means they don't share the same fate. And so one might converge and one might diverge. And yeah, that's what it means.
So could we say that the limit doesn't exist?
Well, yeah, I mean, if the limit didn't exist, that would also be the case. But it's not. It's not. This is a test. It doesn't tell you the value of the series. So it tells you whether there will be a value of the series, and so, for example, if the limit comparison test tells you that it converges, then you might be like, oh, okay, fine. Now let me work really hard to try to figure out what number comes out or what's an approximation for that number. But if you discover that it diverges, then you just stop working. You don't need to do anything else because you know that it doesn't matter how hard you try, it's not going anywhere. But we don't really go there in this class. In this class, we just ask ourselves, does it converge or diverge? That's kind of where we end. So I liked how Robert phrased it, that when that limit exists, it means that these things are somehow close enough together that their ratio is connected, and what that ratio is doesn't matter, other than that it's consistent or that it's constant. And again, think back to the videos, right? That you had Superman, a superhero in the first video, you had Mr. Incredible, more superheroes in the second video, right? The reality is, and Superman does have a cape, I'll give you that, but the reality is that it's not so much who's in the videos. What matters is what are you tied to, right? So if you tie Lois to Superman, they share the same fate. Yay, that's good. If you tie the cape to the superhero in a jet engine, that's bad, right? So the limit tells you whether they're tied together, You have to separately figure out whether that's a good fate or a bad fate. Let's do one more example, and then I think that all this will come together nicely when you practice it on your homework. So here's the example that we were playing with earlier in class, and remember that our inequality went the same way. So now we're going to try our limit comparison test with the sum of 1 over n to the 2/3. And so we can look at the limit as n goes to infinity of 1 over n squared plus 3 to the 1 over 3 and 1 over n to the 2/3. And is it clear that that limit's equal to 1? Is that obvious?
Yep.
Okay, good. So the limit's equal to 1. This means that they share the same fate. So then we would say that since sum of the 1 over n to the 2/3 diverges, then the sum of the 1 over n squared plus 3 to the 1/3 also diverges, same fate, by the limit comparison test. By the limit comparison test. So the limit, that 1, on one of the previous examples, we got a 1, and that meant converge. In this case, the 1 means diverge. Because the 1 doesn't itself mean anything, the 1 simply tells us that they share the same fate. So there's a little bit of nuance that I'm sure you're going to want to play with as you do your homework. But I guess if I had one piece of advice that comes out of this section, the piece of advice would be never use the comparison test unless you absolutely have to. Use the limit comparison test. What we just did is less intuitive. Like, it's a little harder to wrap your brain around, but it's way more powerful. It's way faster. It works way more of the time. So, pro tip, figure out what the comparison test's doing because it's kind of intuitive, but then use this limit comparison test lots of times. And mostly the thing that you're going to be comparing to is either a p-series or a geometric series. So as we wrap up today, I just want to thank you all for all this. Hope your brains don't hurt too much. And then I just hope that all of our fates are the same and that we get to converge together again tomorrow to start working on the alternating series test, which is both easy and even a little bit powerful. So have a wonderful day, everyone. Feel free to hang on the line if you have questions, and I'll see you all tomorrow. Take care.
Robert.
See you, Dusty.
See ya.
Dusty, I have a question. About the limit comparison test. I just look at the note and it said set series with positive terms. So do we need to check it to make sure the terms are positive?
What would happen if this would also work if they were both positive or both negative, so that would also work. But imagine that you had one series was like 1 over n and the other series was like maybe minus 1 over n. Well, I'm trying to think of something really obvious. Because in this case, this one will converge and this one will, yeah, this might work. So in this case, if we looked at the limit as n goes to infinity of 1 over n over the negative of that, right? We're going to end up with -1 to the n, right?
Yeah.
So it's going to bounce back and forth. Boom, 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 boom. And so the limit won't ever exist.
Yeah.
even though it seems like somehow these things maybe have something similar going on. So I think I say that to say simply that I think the important thing is that they have the same sign. So if they were all negative, I think that would also work.
Okay.
But the theorem itself is a little bit more restrictive. Also, maybe you have one series like this that's always positive, but you have another one that you're comparing it to that's sometimes starts negative and maybe ends always positive. In this case, you could simply just chop things off and say, let's just consider the things from maybe the blue line forward, and in which case they would all have the same sign. So the fact that there were a few bad signs isn't going to be a problem for you.
Okay.
Did that answer your question?
Yes.
Okay.
And I have other question about interval test. Actually, it's the same thing. It said f is continuous, positive, and decreasing sinc function.
Right here.
Yes. So do we need to check it's positive and decreasing?
I think that
because in homework
there's probably a few questions where it will come up, but in general, I think unless something weird is going on, I would just say don't worry about it unless it seems like it comes up as an issue.
Okay.
So kind of in general, don't worry about it, but knowing that that's a possible issue will help you to understand what's going on if you end up in sort of a strange situation.
I asked because in homework I take time to check it's a decreasing function or not, so now I can ignore it, right?
Because you'll end up having to take a whole bunch of derivatives, right? And then you've got to show that all those derivatives are always negative.
Yes.
Like the whole goal is it takes a long time.
Yes.
Yeah. And most of the time, if it's problematic, maybe it doesn't work. Most of the time the graph ends up looking something like this. And so if there is a problem, all you do is you chop it off and only go from there forward. So the fact that it wasn't always decreasing doesn't even matter anyway. Like we've got a workaround for that. So.
Okay.
Did that answer your question?
Yes. Okay.
Yeah.
Thank you.
No problem.
Thank you. That's all. See you.
Sounds good. See you, Vu. Jay, questions? Joseph, questions?
I do not. Thank you, Dusty.
Thank you. I'll see you tomorrow.
Yep. Have a good rest of your day.
Yep. Jay, questions?